Hi students, very good morning to all. So, welcome back to physics video class. So far we have discussed about potential due to the point charge and the potential energy due to the point charge and the potential electrostatic potential due to the dipole. So, the expression for that also we have discussed. So, in this part we are going to see the potential and potential energy of the system of more number of charges, that is more than 2 charges. So, first thing is that is potential due to the system of charges. So, we know what you mean by electrostatic potential. So, first of all I want to tell one thing, that is the difference between potential and potential energy. We know the definition for potential energy. So, potential energy is simply the work done in bringing any charge from infinity to particular point of external electric field. So, that work done is stored as the potential energy of that particle at the point. So, similar way electrostatic potential is the same thing, but for unit positive charge. So, the work done for bringing the unit positive charge from infinity to particular point. So, that work done is called electrostatic potential at the point. So, now we move to potential due to the system of charges. Here we are assuming the 4 number of charges. So, in this way we can also imagine the more number of n number of charges also. So, due to these number of charges we can find the potential at any point. So, at a point due to more charges, so whose distance are r1, r2, r3, r4 respectively. So, we know that for single charge the potential formula equal to 1 by 4 pi epsilon naught q by r. So, general formula. So, simple for applying all the charges. So, it is a scalar quantity. So, we can simply adding the algebraic sum of all potentials. So, potential due to these charges, n number of charges at point P can be written as the summation of all individual potentials. So, we can write V1 plus V2 up to Vn. So, substituting the values, so 1 by 4 pi epsilon naught Q1 by R1 plus Q2 by R2 and so on Qn by Rn. So, by simply we are writing summation, taking summation Qi by Ri, where Ri is from 1 to n. So, this is for dissimilar charges. So, Q1, Q2 are different charges. If both charges are similar, so similar and equal, so Q will be equal and we can Q taking outside. So, for that Q is taken outside, remaining will be the V equal to Q by 4 by epsilon naught summation of 1 by Ri only. Here Q is taken out. So, Ri, I from 1 to n. So, this is the potential due to the system of n number of charges. So, if you consider the two charges, so simply adding the 2 potentials. If you consider 3 charges, you simply adding the 3 potential V1 plus V2 plus V3 at those conditions Q by 4 by epsilon naught 1 by R1 plus 1 by R2 plus 1 by R3. So, next we move to for spherical cell. We know spherical cell means it is a conductor. So, we know the electric field inside the spherical cell will be 0. The previous lesson, first lesson we have discussed. So, in this lesson for potential, so consider a spherical cell of charges, charge configuration will be Q. The charges on this cell is Q. So, due to these charges we are finding the potential at any point outside, surface and inside of the spherical cell. So, for that we consider the origin of the cell and consider the point P. So, at this point P, due to this spherical cell the charges Q, we can write potential at point P equal to V equal to 1 by 4 pi epsilon naught Q by R. For due to the single charge formula, we know that same formula we can apply here. Here Q is the total charge of this charge configuration on the spherical cell. So, on surface, so considering the point on the surface, so the distance will be capital R, that is equal to the radius of the spherical cell. So, in this condition V can be 1 by 4 pi epsilon naught Q by capital R. Here capital R equal to, that is here R equal to the distance between the points equal to capital R. So, on surface. Next we move to inside. So, inside we know E equal to 0. E equal to 0, electric field will be 0 inside the spherical cell. So, if E equal to 0 means so the charges on the surface will be similar charges. So, automatically electric field will be 0 inside. The first lesson we have discussed. So, if E equal to 0, then there is in all points the work done for bringing the charge from one point to another point. From one point to another point equal to 0, work done equal to 0, which means the potential energy at all points will be equal. So, we can write V equal to constant. So, the potential equal to constant and E equal to 0 and work done also equal to 0, then potential energy equal to constant. So, these are the things we can consider inside the spherical cell. Simply E equal to 0 and V will be constant. So, at all points electrostatic potential will be same. So, these are the potential due to the system of charges and for spherical cell. Next we move to potential energy of the system of charges. So, I initially told the difference between potential energy and potential is nothing but potential energy for particular charge Q. So, potential electrostatic potential is we have to assume the unit positive charge plus 1 coulomb. So, potential energy of the system of charges. Consider a system of charges Q1, Q2, Q3. There is 3 charges are taken and here first consider Q1 in order to bring this point R1. So, and this position will be R2 and this position will be R3 from the origin. So, if you draw the position vector, so which gives the R1, R2, R3 the positions, and first initially we have to bring the Q1 charge from infinity to at this point. So, in this condition there is no electric field previously. So, without a electric field, so the work done from bringing infinity to Q1 equal to 0. So, that is work done equal to 0. So, only we have to consider in the external electric field, then only work is done. So, otherwise work done equal to 0. So, for bringing Q1 from infinity to at point R1 equal to 0. Initially work done is 0. So, potential energy corresponding this energy will be also 0, but it will produce the potential at all points. So, now it is brought to here. So, due to the Q1 charge it will produce the potential and electric field around it. So, that potential can be written as similar way 1 by 4 pi epsilon naught Q1 by R1p. P is at any point. So, due to this charge the potential at any point, the point may be anywhere else, that point is P. So, that is called R1p. So, for Q1 work done equal to 0 and potential of Q1 will be V1 given by this. So, now consider the second charge Q2. So, we have to bring the Q2 charge from infinity to at the point, this is R2, position R2. For that now we have to do some work against the potential of Q1. So, already Q1 is present, so electric field is there. Now, move to Q2 from infinity to this point. So, we have to do work against this potential. So, that work done equal to, already we know, W is equal to general formula, W is equal to QV or VQ, we know, that is it is from V is equal to W by Q. So, we can write W is equal to VQ. So, this is the we can write for charge Q2. So, work done equal to V1 of R2 into Q2. So, Q2 is the second charge we are bringing from infinity to at this point, and V1 of R2 is the potential due to the Q1 at R2. So, for simple W is equal to QV or VQ. So, work done equal to same way we are writing. So, here potential is the due to the first charge at the point R2 and the Q2 is the charge moving from infinity to that point. So, we can write work done equal to V1 of R2 into Q2. So, V1 of R2 is here, that is potential due to the first charge and second charge is there. So, totally we can write 1 by 4 pi epsilon naught Q1 Q2 by R12, where R12 is the distance between Q1 and Q2, this distance. So, we can write R12 equal to R2 minus R1 from origin. From origin the distance for Q1 is R1 and the distance to Q2 is R2. So, R2 minus R1 gives R12. So, that is the work done for second charge. So, also the potential. Now, two charges are arrived at particular points R1, R2. So, now due to these two charges, some potential will arrive at all points around them. So, if you consider any point P around the two charges, first two charges, the potential at that point is taken as V of 1, 2. The potential due to first charge and second charge Q1 and Q2 equal to 1 by 4 pi epsilon naught is common, and so Q1 by R1P. So, this is due to the first charge, and Q2 by R2P, this is due to the second charge. So, this way we can write the potential due to two charges. Now, consider the third charge. If you bring the third charge from infinity to this point, now we have to do work against the both charges and also against the potential of both charges. So, for that, for taking for Q3 work done equal to same formula, W is equal to QV or VQ. So, here V of 1, 2, because third charge is bringing, before that two charges are there. So, due to the potential due to two charges is there. So, V of 1, 2 point R3. So, we are bringing the Q3 from infinity to this point, that is R3 from origin against the potentials of Q1 and Q2. That is why we are writing V of 1, 2 at R3 into Q3. So, substituting the value of Q3 and V of V1, 2 of R3, so we can obtain this value 1 by 4 pi epsilon naught, simply Q3 by multiplying this. So, Q1 Q3, Q2 Q3. So, this is the work done for bringing the charge Q3 from infinity to this point. Now, three charges are assembled. So, total work done we have to calculate. So, the total work done for assembling the three charges is called the potential energy of the system of that three charges. So, we can write total work done equal to the work done for assembling Q1 plus work done assembling for Q2 and work done assembling for Q3. So, initially we know WQ1 equal to 0. So, remaining for these two things we are calculated work done for Q1 and Q2 for work done for Q3. So, substituting all values, finally we obtain the work done for assembling three charges, which can be called as work done, the potential energy of the system. So, finally we can arrive this formula simply substituting these two values. So, this is the potential energy of the system of three charges. Next we move to equipotential surfaces. So, what do you mean by equipotential surfaces? The name itself suggests that the equal potential. So, consider a point charge, single charge plus Q. So, due to the charge, so we can assume the concentric spheres around it. So, these concentric spheres are called equipotential surfaces because the points on the each surfaces, the potential will be equal. So, that is why we calling equipotential surfaces. So, similar way this surface, the all points on those surfaces will be equal potential. So, these surfaces are called equipotential surfaces for the single charge plus Q. So, we know the formula V equal to potential, we know 1 by 4 pi epsilon naught Q by R. So, if R is constant, if you consider this surface, the points all are the same distance from the center. So, same distance from the center, all points will be. So, if R is constant, then V also constant. So, that is why we are telling the points on the surface will be constant potential and they are called as equipotential surfaces. So, this is for plus Q single charge. The similar way for uniform electric field, we can say for uniform electric field means the electric field at all points will be equal, and the consider two surfaces here perpendicular to the electric field. So, the points on these surfaces will be equal potential, and also this surface the points on all the potential will be equal. So, these are called equipotential surfaces for uniform electric field. And the another way, the electric field of the charges we know, for considering the positive charge, the electric field lines will be always outwards away from the charge. So, for negative charge they always inwards towards the charge. So, whatever else, the electric field lines and the electric field is always perpendicular to the equipotential surface that are crossing at that point. So, electric field is always perpendicular to the equipotential surface at the particular point. So, this is called equipotential surfaces. A similar way we can draw the equipotential surface for various configuration, charge configuration, that is system of dipoles, equal and opposite charges, or system of various charges, similar charges for dissimilar charges also we can draw the equipotential surfaces. Now, let me explain what is the relation between the electric field and the potential. So, we know very well about what do you mean by electric field, what is electrostatic potential. So, now we are relating both by using the formula. So, that is very important one here. For that you are assuming that two equipotential surfaces A and B, whose potential of A is V and the potential of B will be V plus del V. So, there is a potential change in potential will be del V, the difference in potential, and the electric field direction is this direction, electric field is towards the upward. So, and points, consider the points R in surface A and P in surface B. So, assume a unit positive charge bringing from point P to R in the direction opposite to the field. So, we have to do some work for that. So, in bringing unit positive charge from point P, that is from surface B to surface A against the electrostatic field E. So, we have to do work, that work is called, we can calculate by using formula. The work is normally we know force into distance, here force equal to electric field into charge into distance will be del L, distance between both points is equal to del L, and we can write, we are saying charge will be unit positive charge. So, here Q is unit 1 plus 1 coulomb is moving from P to R. So, Q equal to 1. So, we can write E into del L. So, modulus only magnitude. So, E into del L. So, this is also equal to, so this is the work done for bringing a unit positive charge from P to R, that is from surface B to A, both are equipotential surfaces against the electrostatic field E. So, which is equal to the potential difference between these 2 points, potential difference. We can also explain in the first session, first part, the potential due to the point charge. So, here we can write VA minus VB. So, this work done is equal to the potential difference between, that is change in potential between the two surfaces. So, substituting the VA VB values, that is V minus of V plus del V. So, we can write V minus V minus del V. So, minus del V. So, in order to know electric field only, so minus del V, del L comes here, del L. So, otherwise we can write, which is equal to plus modulus of del V divided by del L. Here we can write R E equal to, we can write like this. So, electric field equal to minus del V by del L. So, this is the relation between the electric field and potential. E is the electric field, V is the potential. So, from the equation we can define the relation. So, electric field is equal to the negative potential gradient. Again I am telling, E electric field is equal to negative potential gradient, which means the electric field and the decrease in potential. If the electric field is in this direction and the towards we moving electric field, the potential increases. So, and in the direction of electric field potential decreases, because here higher potential, this is lower potential. So, if you move towards the electric field, the potential decreases. So, we can write modulus of del E equal to minus del V by del L, and also we can write modulus of E equal to plus del V by, only consider a magnitude. So, del V by del L. So, and again we can calculate, if del L equal to 1, which means del L is the distance, if it means 1 equal to, so unit displacement, if del L equal to 1, then E equal to minus del V. So, which gives the electric field is equal to the potential for unit displacement. So, decrease in potential for unit displacement. So, E equal to minus del V if del L equal to 1. So, in this way we can define the electric field with relating the electrostatic potential. So, this formula is very important. So, students, just you do the practice by doing examples and exercise and go through the NCERT books.